Hey, hello, welcome here to yet another online lab and another one involving our circuits and our electronics. And so as we saw last week, you might remember we did the, the potentiometer, and we made a homemade voltmeter is what I kept calling it. And like I said, that was a real exciting one to me. And this one is almost as exciting to me because today we're going to build what I would call a homemade ohm meter. We're going to build a little device that can measure resistance. And like last week, we made a homemade voltmeter, and we used that as an opportunity to kind of show you things like, and there was all kinds of fun things in last week's lab, like internal resistance of a battery, that difference between a terminal voltage and an EMF. We did Kirchhoff's loop rule in order to get the current and solve it, and collected some data. So hopefully you got a lot out of that lab, just like hopefully you'll get a lot out of this lab, even though, like I said, it's probably a little better if you were here in person, able to hook up the wires yourself. But I'm hoping that by seeing me do this, at least you'll be pretty close to hooking up the wires yourself when the day comes, because this pandemic won't last forever, I trust, and we'll be back into the lab and doing hands-on. And so in your guys' case, probably that would mean as you transfer on, you will be at the four-year university and be asked to go into lab and start hooking these up, and you'll hopefully be close enough to be able to kind of figure it out once you get there. That's the hope. That's why we're still trying to get these online labs and get them as hopefully successful as possible. All right. So, as I said, we are going to build a homemade ohm meter. You can think of it that. It was designed by a guy named Wheatstone, and so it's called the Wheatstone Bridge. You'll see why it's called a bridge. When you draw it on the board, it kind of looks like a trestle bridge, and it's kind of neat, and like I said, it's got some neat features. So we're going to do that and hopefully learn some electronics along the way. So I will say, if you've got your lab manual, and I know you do, the PDF form anyways, on page 21 is the start of this. And so like last week, I'd kind of encourage you to kind of review for yourself things like resistors in series and resistors in parallel, and Kirchhoff's loop rules, and the junction rule, what I call the conservation of energy and conservation of charge. But he goes through all this, and I want to run through most of this with you. And he's got a nice looking circuit on page 23, and that's what I'm going to hook up. Now ours, I must say, are a little different, and I would say the same thing if you were here face to face, because this circuit kind of shows our old equipment, and we've got some newer equipment that makes it a little different, even a little easier to hook up. Then on page 24, he actually shows kind of the physical layout of our equipment, so I'll show you that on video. But take some time to read through that, and I'll go ahead and run through it also here in a second. And so I'm going to start the video here on page 24, where it says step 1, and it says construct a simple slide wire Wheatstone bridge. All right, so let's talk about this. Let me grab my marker here. And you might remember from last week, we made a 2-meter potentiometer. This week, we're doing Wheatstone's bridge, and it kind of starts out as a 1-meter potentiometer. So let me do like I did last week. Let me put point A. Let me make a long looking resistor here on the whiteboard. This will actually be a wire that is 1 meter long. And so if you kind of look at our equipment today, it's a little different than last week. Last week we had 2-meter sticks because we wanted it to represent 2 meters. This only has a wire across 1 meter. And so that's what I meant by a 1 meter potentiometer, essentially is our starting point. And if you remember last week, we hooked it up to 2 volts because we had 2 meters. This week we have 1 meter, so we're going to hook it up to 1 volt here. And so if I take a power supply and hook that to point A, the lower potential, and this to point B, the higher potential, and set it to 1 volt, I will get the same amount of current going through the wire like we did last week. Now, of course, last week was also online, so you didn't get a chance to touch it, but I think I made a comment in the video that if we turn up the voltage too high, we damage the wire, and that has happened in the past, and also it gets red hot and people burn themselves. So the rule I like to say when we use our nichrome wires is, you know, make 1 volt for every 1 meter. So if we're dealing with 2 meters like we did last week, we will have 2 volts. This week we're dealing with 1 meter, so we will have 1 volt. So I shall begin here by turning on my power supply again. It's still set at 2 volts roughly. And so let me, where's the course adjustment here? Turn it on down so that it is at 1 volt. And so let me hook up, and I might need a little longer wire here, but I'll put the negative here. And so that is the connection, which on the diagram I'll call point A. And way over here is point B. Point B, I need one of the longer wires. I'm going to run over here and grab one of the longer wires. Actually, I'll grab a couple just in case I need some longer ones. But I'll even move that a little closer and put this on the sidelines here, and I think we'll just make it. There we go. And so there is my first part of my Wheatstone Bridge. And the current is flowing, and I should get a little bit of current. Good. And let me just kind of put those off to the side. But there is my current and my 1 volt. I like to just kind of double check this. And let me just go ahead and put a connection here and a connection here, and just make a comment about the DMM again, the digital multimeter. Remember that we think these two on the right when we want it to be a voltmeter, and we hook voltmeters in parallel. I commented on it last week, and the week before that with Ohm's law, I was trying to point out that you hook voltmeters in parallel, but ohm meters in series. We haven't done any ohm meters other than Ohm's law, but that's going to change next week. And so next week we're going to be hooking up this DMM as a voltmeter, and then switching it to an ohm meter, and then switching it to an ammeter. And there's going to be a lot of different changes. In fact, that is the whole point, or not the whole point, there's many points, but one of the big points of next week is to make you keep switching back and forth, so you'll really get in the habit of knowing how do you hook up a voltmeter versus an ammeter versus an ohm meter. Well, I'm getting ahead of myself because that's next week. But this week then I have this, and I want to use it as a voltmeter and also as an ohm meter. And so we'll talk about an ohm meter, but right now I'll just hook it up as a voltmeter. So remember these two in parallel, and the second click is voltage DC, and I should have 1 volt. And so I do. Now, as you'll see, the exact voltage isn't really that important. So I was not hooking it up really to show you that we need to be exactly at 1 volt. I was hooking it up just really to remind you of this is how you do a voltmeter. Because one of the things I'm concerned about in these online labs is, since you're not actually hooking them up yourself, you're not gaining that experience. So I think the more I keep saying it, the more you'll be able to do it when you actually have to do it yourself. Because it is a little tricky. And you guys in the circuits class are probably discovering that right now, because I know in your circuits class you guys have bought, as part of your equipment, a DMM, and you got to do these at home, and so you're hooking them up as voltmeters and then as ammeters. And I know in the past that has been a big part of my job, walking around and stopping at students and saying, you know, they're having troubles, and I have to say, well, you're not hooking it up right. And so anyways, remember this: voltmeters, these two connections on the right, and in parallel. All right, so I can disconnect this because we're like I said, good with that, and that was a nice review of what a voltmeter does, because I'm going to switch it to an ohm meter real soon, and that's kind of a new instrument for us. And so again, that's why we call it a DMM, a digital multimeter, because it measures many things. Well, back to the Wheatstone Bridge. So here's the power supply, but in addition to that, we're going to split off and run a parallel branch. And so you might say that these two resistors are in series with each other, but the two collectively are in parallel with the wire. Okay. Now, looking at your author's picture, he calls this, well, bummer, because he calls this point A, and so maybe I should get rid of that. And he calls the two endpoints M and N. Okay. Let me just make sure. He calls M on the positive side, so here's M, and he calls this N. Okay. Then, looking a little closer at this drawing, from M to A, he refers to this as resistor R1, and he refers to this one here as resistor R2. And the neat little setup of this Wheatstone Bridge circuit is that if you know one of these, you can then find the other. So that's what we're going to do. We're going to start with what we would call a standard. Let's define a standard. And for us, we've got this little box here. This little box has a known resistance of 45 from here to here and another one of 1. You'll see why we have two of them. We'll only do one at a time. So let's start with the 45. So this is a 45. So this will be the known one. And I just need to check. I think your author says that R1 is designed to be the known one. Okay. So let me put here that this is known. We know what it is. And at the moment, it is 45 ohms. Later on, as we get through the lab, we're going to switch it to 1 ohm. And it's not so much that we really need to change the resistance. It's just, as you'll see the way this is set up, we can measure things more accurately if our known is somewhat close in value to our unknown. And so we're going to be asked to measure values. The first 3 of them are going to be near 45. So that's why I want to use 45. And then we're going to be asked to measure 5 more, and they're going to be close and actually, well, a near 1 ohm. Some of them are under 1 ohm and some of them are more than 1 ohm. They're around 2 ohms. So that's why we're going to make that switch. But the thing I want to emphasize is R number 2 is unknown. And if we hook everything up right, we can find out what this value is, number 2, based upon knowing what our number 1 is. And that's why I said what we're going to make is a homemade ohm meter. And then we will use the professional ohm meters to see how close we got. And so we'll keep our fingers crossed that we get something decent, something close. All right? And I'm debating, maybe I should save the calculations for you guys, but I know when I get there, I'm going to be curious myself and go, oh, how close did I get? All right. Now, let's keep talking about how this thing works. Do you remember last week we had this thing called the galvanometer? I have it again here. Here it is. This galvanometer then deflects one way or the other depending on if current is flowing. And what we're going to do with our galvanometer is something like this. Here's where it begins to look more like a bridge. I'm going to connect the galvanometer at point A, and I'm going to put a wire at the end of this galvanometer, and I'm going to touch it somewhere along this wire. And like last week, I'm going to be looking for the magical point. The magical point would be the place where the galvanometer does not deflect. Now, just to label this, your author calls this point B. And so I will call this magical point B here. And we're going to have to hunt for it. So in other words, we'll just come up and touch the wire right here. Chances are we won't find the magical point just first try, but we will see it deflect. And depending on which way it will deflect, we will move our contact point until it no longer deflects. Because something very interesting happens when it doesn't deflect. This is a null reading. Okay? And so when it doesn't deflect, what's special? And what's special is this. As the same we discussed last week, is when you touch it at point B such that it doesn't deflect, you can say that the voltage at A and the voltage at B are the same value, right? Remember we said that if they're going to be fighting each other, if A had a higher voltage than B, this would force current down this way through the galvanometer. And that would be the positive direction, and the galvanometer needle would move positive. But on the other hand, if point B is at a higher potential than point A, this part here would force current back up to A. And so whichever one is at a higher potential. And we then, of course, if we see the needle move, whether it moves positive or negative, we know we're not at the magical point, and we know which way to move to get to that magical point. So let's just pretend I'm at this magical point for a moment. Let's say that I am touching it at point B, so there's no deflection. And here's what I would say. Watch the current here. If the current comes out of this power supply, let me just call it current naught, the initial current coming out of the power supply. As it goes along the circuit and it gets right here to this node at point M, some of the current is going to go this way. Let me call it current number 1. And the rest of it is going to flow this way. Let me call it current number 2. Now there's a couple of important things about this magical point. So if you watch current number 1 and we're at magical point, notice the galvanometer is not deflecting, and that means none of the current in number 1 goes up through this galvanometer, or none of number 2 comes down. So that means on this half we still have current number 1. And the same logic applies up here near the top. If current number 1 goes through resistor 1, and again the galvanometer is reading 0, that means nothing goes through here. So the current that continues on through resistor number 2 would still be current number 2. And so again, that magical point has something very, very interesting. Because if you run through the math here, what you are saying is the voltage change from M to B would be the same as the voltage change from M to A. Maybe I'll write it this way. The voltage from M to B would be the same as the voltage change from M to A. Now, so I can kind of apply Ohm's law. Let's do this. This nichrome wire that is 1 meter long, and I'm touching it at its magical point, I could say this much is a resistor, and this much over here is a resistor. And they're in series, so the sum of the two is the whole resistance of them. Let's call those resistors 3 and 4. Now, I hesitate to write it because I want to come back here to the drawing to make sure I labeled number 3 correctly. And your author says 3 is from M to B. So from M to B is number 3. And then from B to N is number 4. And I'll just Make sure I got the same symbolism there. Okay. See, the reason I want that is, look at this. And let's go back to Ohm's law. This says the voltage between MB, right here, which would be calculated as current number 1 times resistor number 3, would be the same as the voltage change from M to A. Well, using Ohm's law, that would be current 2 over resistor 1. The other half of it is also true. The change in voltage from A to N would be the same as the voltage from B to N. Well, so let me write this. The voltage change from B to N would be the same as A to N. All right, now if we apply Ohm's law, B to N, so B to N would be current number 1 times resistor number 4. And the voltage change from A to N, again, using Ohm's law, so A to N would be current number 2 times resistor number 2. And then here's where the neat little math comes into play, and the whole Null reading and the Wheatstone Bridge has its strength. If I take this second equation and divide it by the first equation, then current number 1 cancels off, and current number 2 cancels off. And so it doesn't really matter what the numerical value of 1 and 2 is. The only thing that matters is that we are at this magical point where no current went through this part of the bridge. That is, the galvanometer was reading 0. That was the magical part that kept the current number 2 the same after it went through point A. And then likewise kept current number 1 the same on the other side of point B. If I rearrange this equation to solve for the unknown, it looks like this. R2 is then equal to R1 times R4 over R3. Now, I'm not quite done yet, but here's what this says. This says that I could get the unknown, remember R2 is the unknown, from the known, there's R1, and the ratio of these two resistors. Well, let's keep going here, because here's where the beauty of resistivity comes into play. Remember, R3 and R4 are actually the resistors set up by this nichrome wire. See, that nichrome wire has the length of 1 meter, but it's actually the same material with the same diameter. So I could describe resistor number 4 as the resistivity of that wire times the length of number 4 divided by the area. Now, maybe I should come back over here to the picture. What I mean by the length of number 4 is how far is it from N to B. So the length of number 4 is this length from L to B. So that's why it's going to be important for me to know where I'm touching it. And that's why it's mounted on a meter stick, so I can easily measure what is the length of B to N. And then likewise, look at resistor number 3. Resistor number 3, again, would be the same material, the nichrome, times length number 3 times the area of this wire. Now, coming back to this picture, what do I mean by length number 3? Well, I mean this. I mean the part of the wire that would be from the length from M to B. Now, obviously, length number 3 plus length number 4 must be 1 meter, okay? But I guess that's useful in the sense that I only have to measure one length. And maybe I'll just measure length number 4. And then, of course, from that, I can get length number 3. But watch this. Here's where the kind of the neat design of the Wheatstone Bridge comes into play. Since we're using the same material, in this case nichrome, it cancels off. So it doesn't really matter what material we use. And as long as it's the same type of wire with the same diameter, that too cancels off. And we end up with what I'll call the working equation for today, which says simply this, that you can find the resistance of the unknown, and that's what we're going to do. That's why I called this a homemade ohm meter. So we're going to find R2 based upon a known one, R1. And then also by measuring the length, and like I said, I'll just measure L4. And then, of course, once we have that, you also have L3. And then, of course, once you have those, you can get out your calculator and you can calculate the R2. And that's really step 1. Let me turn back to step 1, because I think step 1 says construct the Wheatstone Bridge. Oh, I guess I haven't constructed it yet. I've just kind of talked about it in theory. So let me construct it here. Let's actually do step 1. So the only part I've done so far was this power supply and this wire here. And so here's the plus, and so this right here is point M. It goes across the wire, and so this right here is point N. And so I've done this much right here, power supply and wire. Let me do the top half. So here is the known, and the known goes from point M. So again, this is point M, so I'm going to put it kind of right here for my setup. Maybe I'll put that in there. So there's my known. So there's R1. And then my unknown, and here's what we're asked to do. We're asked to measure, and I still have to read step 2 to you, but it says pick these 3 near the bottom of your circuit board. And so here's this has 5 resistors, but we just have to use 3 of them. So we'll use these for, so I'll start with this one here. And so I'll just set it maybe right here for a start. And let me grab a couple of wires so I can actually kind of hook this up. I don't need them quite that long. But if I've done this correctly, it says go from point M to R number 1, so there's R 45. From the 45, and so this wire is kind of point A, so A. Go to the unknown, so this is going to be my one I'm building, my unknown, number 2. And then from here, back to this side, which is point N. Okay, so I think I got it. At least I'm not quite done. I've got the upper part of the bridge. And then, of course, I've got the galvanometer. And the galvanometer says go from the middle between these 2 resistors and go through the galvanometer and then put in your little tap switch to touch it. Okay, so let me find my galvanometer. Here it is again. And let me find another wire. And so here's a wire. And it says point A. And so point A is kind of this point right here that's between the 2 resistors. This one feels kind of loose. I'm worried about that one. Let me grab all right. So here and here. Now it feels better. Okay, so this wire is point A. And of course, in my picture, it kind of looks like I'm supposed to plug it right here. But as we commented before, remember a wire is an equipotential. So I could plug it here. It doesn't have to be right here. Or I could plug it here. It doesn't really matter. So I'll just plug it there. So that's point A. And so point A starts here and goes then to the galvanometer. And so I will hook it to the galvanometer. And then, of course, from the galvanometer to, and this is how we'll kind of hunt down the magical point right here. And we'll do the little tap switch thing. Okay. And maybe for starters, just to see if things are working well, I'll go ahead and hold this one in my hand so I can both see it and you can see it, and I can tap the trigger switch here. But I'll hold this down and I'll just start with right in the middle and then see what happens. So if I do that, you'll see the galvanometer moves towards the negative side. Now the negative side means that current then is flowing this way and making the needle go that direction. And so that tells me point B is at a 2 of a high potential. Okay? And so lower potential would be over here somewhere. So maybe I'll just put it at the 30 mark here for a second and kind of show you again. So I'll hold it against the metal wire at the 30, push the button. Now it goes positive. So again, if it goes positive, it's telling me that point A is at a higher potential than B and current is going this way. So I need to move the wire to this magical B point. Maybe I will do at 40. Now the 40 means from here to here. So this is really this distance, the L4. And so if I touch here and push the button, ooh, it's looking pretty good. Or did I not get a good contact? I think I'm just not getting a good contact. There it goes positive. So if I move it back, that looks like that's going to be the magical point, which is the 40. Go figure. Okay, but I didn't mean to find the answer quite yet. I meant to just kind of demonstrate, because this is what step 1 is. So I would say I'm now done with step 1. Let me come back to the instructions here. So procedure step 1 says construct the simple slide wire Wheatstone bridge. So I would say I now have constructed a homemade Ohm meter. And so like last time, I don't know, there's just something exciting about it to me. There's no dials, there's no numbers, but yet it's so simple. I don't even have to have a perfect voltage. I don't even have to have a perfect current. All I really need is a galvanometer, and the accuracy is based upon distance. And of course the quality of my equipment. But that's the really neat thing. So I would say I have now built a homemade Ohm meter. And so now I can actually really start to measure something. So here's what it says. It says, number 2 says, determine the resistance of 3 copper wires, or, well, let's just stop there. Carbon wires, because that's what I have here. So those bottom 3 are where I'm gonna do. And says it use your bridge, that is your homemade one, and your known resistor of R1, which is 45. See what resistance you get for these 3, and then check it with the professional Ohm meter to see what you get. Okay, so if I come over here and start writing in our first set of data, I will say, okay, number 2, R1, R2, getting ahead of myself, R2, and R3. What is the resistance I get with, and let's do it both ways. I'll say, what is it with the one we're going to make? Let's call this the laboratory Ohm meter. Okay, the one we make. And then let's compare it to what did we get from the pro, the professional ones. I'll just put pro. And so let's see what kind of numbers we get. Now I'll double check this, but as I said, using this working equation, I just need to say, okay, I need to measure just one distance. And L4 is the really good one to measure, because L4 is from this N to this B, which on my equipment would be from this end of the meter stick out to where I'm touching it. Okay? And so I am touching it at 40. So if I come over to my little calculation here, I would should probably add something here. This L4 is 40 centimeters, which means the L3 is the 60 centimeters. Now, I said I wasn't going to calculate these, and I won't, but maybe both to help you and to settle my curiosity, let's see what kind of number I would get. And so if I grab that working equation and say R2 is R1 times L, which one's on top, number 4, over number 3, I would say that I have 45 ohms as my standard, my known one. Then I have a 40 over a 60. And so I have 45 times 2/3. That's a 15 times a 2, and so that's a 30 ohm. And I probably shouldn't do all of these so that you have some work to do. But my homemade ohm meter has just given me a value of 30.
R1, R2?
Oh, thank you. I did something absolutely terrible here. I am really, really sorry. This is actually R2, R2, and R2 because they're all R2s. We're going to change R2. We're going to try to find the unknown. Thank you for pointing that out, Ron. That could have been really confusing on video. Okay, let me come back here and clarify this. Look at this picture here for a second. All right, this R2 is where we put our unknown. And so we're going to do that for 3 different resistors. So these 3 different resistors are all going to be R2. But we're going to do it 3 different times. So let me come back over here and call this R2A, R2B, and R2C. How about that? And so my 3 resistors I'm going to measure are A, B, and C. But they're all going to fit as an R2 in my Wheatstone Bridge. Good. Yeah, that could have been confusing because I was using 1, 2, and 3 for a different labeling than I did over there. Okay, so I have really found what I might call R2A. So R2A is 30. So my homemade ohm meter is R2A. Now, I'm going to use this as an opportunity to say then, how do we then use one of these DMMs, digital multimeter, as an ohm meter? Okay? And so let me start with it in the off position. And let me pull out the wires, because when you get your chance to play with one of these, some of these multimeters have many connections. And you know you need 2 of them, but which 2? And I'll say it again, like I said, they're in this case it's the lower right-hand corner, but it says common. The common connection is always used. It doesn't matter how you have it set up. As a voltmeter, an ohm meter, or an ammeter, you always connect it to the common. Okay, so that's the easy one. The harder one, you got to kind of scan the other connections, and they tell you which it should be. And as I pointed out, the one right above has the symbol V. So I would put the second wire here for a voltmeter, but it also has the ohm symbol, so I'd put it here for the ohm meter also. Also has the diode, so I'd put it here for the diode meter. Now, for the ammeter, I would use one of these two. And this says use it for things that are 300 milliamps or less, and use this one for your bigger currents that are 10 amps or less. So I would use these connections as an ammeter, and I would call it low current ammeter and high current ammeter. And this one here I would use as a voltmeter or an ohm meter or an diode meter. All right, so I am going to connect it like this, but point out, even though the wires look like I'm using a voltmeter, I am not. I'm going to use an ohm meter. And of course now the difference will be connecting right here. Click, 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 click. And on this model, it's the fourth click, and it points right to the ohm symbol. And it says now you have this to measure as an ohm meter. So an ohm meter is almost like a voltmeter. Of course, they measure different things. An ohm meter measures the resistance, and a voltmeter measures the voltage. So the setting on this dial is different, but the wire connections are the same. But here's what is very, very different when you go to connect your wires. Okay? If you remember me saying a voltmeter, you just take the two wires, and when you're hooked up to a circuit like this, if this was a voltmeter, I would just plug it in and get the voltage. They'd be in parallel. And so that's how a voltmeter works. You hook a voltmeter up in parallel when you have it connected to the circuit. I mean, obviously, you wouldn't try to measure the voltage if you weren't hooked to the circuit, right? But an ohm meter is a little different in this sense. You don't want power either on or even connected to the circuit. Because what happens is the little computer on here actually is its own power supply. And it runs a little voltage and measures how much current, and from that takes the ratio to get the resistance. So if you have it hooked to a power supply while you're doing that, the current that runs through the circuit is more complicated than just its own little power supply. It's also coming from this big power supply. So here's what I mean by that. For me to use this professional ohm meter, I want to come over here and disconnect the one I want to measure from the circuit. I still want to hook it in parallel. All right? So ohm meters and voltmeters are actually hooked in parallel. They actually use the same connection on the meter. But what's different is the different setting on this dial and whether it's hooked to the circuit or not. Okay? And we're really going to emphasize this next week. Next week, like I said, it's an interesting lab, a lot of pieces, but one of them is the author is constantly asking you to switch from an ammeter to an ohm meter to a voltmeter, and you got to know how these things hook up, and they're a little tricky. And so that's why the author has you do so many of these next week, because you've already learned now about an ohm meter, an ammeter, and a voltmeter. Anyways, so if I've done this right, I have now hooked it up. See, I'm not hooked to power. I've hooked in parallel, and according to this meter, I get 30.2. So let me come back and fill that in. And so my professional one says it's 30.2 ohms. And maybe I should just put ohms in the top of the table so I don't have to keep writing the units in the table itself. And I did that for the centimeters. Okay, good. So I would say I'm pretty close, right? And so my homemade one and my professional one then agree. And hopefully that will happen all the way through the lab. So let's try that with the other two. So as long as I have it disconnected from the circuit, and I've got my professional one right here, why don't I just move up here to what I'll call number 2B, and say, okay, my professional meter says it is 42.0. Okay. So 42 ohms. And let me move up to R2C. Too bad we don't have a fourth one. Right? Then we can have an R2D2 also. Oh, that was terrible. Okay, so this is number 3 that we of our unknowns, and the professional meter tells me it's 58.8. Okay, so 58.8. So again, those are the 3 values I get from the professional meter. What I will do, and I'm going to force myself not to calculate it, is why don't I hook up in my homemade one and give you L4. I will let you then calculate L3 and what the homemade one gives you, and hopefully those are really close. And so let me just hook up number 2 to my homemade ohm meter. Okay, so let me disconnect the professional one. I'll put that to the side. We're going to need that a little bit later. But let me come back to my Wheatstone Bridge. Let me hook up number 2 there. Let me play the same game. And for a little more accuracy, I'm going to turn this towards me so you won't be able to maybe see the needle here. But that way I won't shake it, and I can just do something like tap that and push that. Whoa, goes way positive. So let's see, way positive means current is going this way, so I've got to increase the voltage on this one. So let me go this way, push it down. No, did I say that backwards? I did say it backwards. Okay, it's acting like I'm not getting any connection. Ah, much better. Let me just tighten these up. I know that's a problem in the past. Okay, so let me kind of hunt for it. Yeah, so that's a little negative. And it looks like maybe right there is my 0 reading. And it looks like I am at a 46.9. So 46.9. Now, I told myself I'd try, but I just can't. I'll tell you what, I'm not going to write it down. But I'm curious how this comes out to be. So 100 minus 46.9 is number 3. So if I go 46.9 and divide it by length number 3 and multiply that by the known 45, I get reasonably close. All right. But it was jumping around so bad, I wanted to make sure I at least got reasonably close. I'm kind of curious. Yeah? Yeah, that's what my home one is saying. Yep, and I'm getting the same number. So I'm going to call that good, and that one's a little further off than the other one. But hey, it's a homemade ohm meter, so I'm just impressed that I got that good. All right, so now let me go to the third one here. And so the third one, you know what, out of curiosity, let's try this second one again, because now that I tightened up the wires, maybe my first reading of the homemade one was a little off. What did I get before? 42? Oh, I like that a little better. So I'm going to put 41.2. I think it just needed some tightening in it, but I don't think the resistance was the resistor as much as or some of it was the connection. So this says 41.1, and that'll make it a little closer. So 41.1. But all of these probably, we should just go through our whole set and tighten them up. Oh, see, look, now it went down to 40.9 when I tightened it up. Oh, now it goes to 42. I'm going to leave that one alone. Okay, it keeps changing. That one we should really swap out for a better one. It's just not making a good connection. All right, so me again try my homemade one here. And saying, all right, what is the resistance of this one? And again, I'll do that. Notice it goes very positive, and so if I kind of slide around here a little bit, right about there. Well, I'm back a little bit. Right there. All right, so that would be 56.5. Okay. So I have a 56.5. And just to make sure things aren't too far off, but I'm going to let you calculate it. 100 minus 56.5. So R4 is 56.5 divided by R3 multiplied by 45. Oh, that one's a nice one. Okay, good. And so that was real close. So I'm happy so far with my homemade one, and it double checks. And in fact, that's kind of the nice thing when if we were doing them live, I'm debating if I leave that to you, but in a live setting you would actually calculate them, and if they don't match, I would say go and give it a try, because you're doing something wrong. Maybe it's the homemade one, or maybe it's even not using the professional one right, but let's figure it out, and then we learn from that. Okay, well, so there's step 2. Let me continue on here. Step 3 says verify that the expression for putting resistors in series and resistors in parallel works. Check your resistance with both your homemade ohm meter and the professional one. Okay, let me do this. Let me clear off my calculations here. And let me just also extra emphasize that you need to finish these calculations. You need to put in the L3s, and you need to put that and make a little table, and that's going to be your step 2 of your lab. Here's what step 3 is saying. It's saying, what if you put resistor number 2A, resistor number 2B, and resistor number 2C in series? Now, just as a recap, and maybe I shouldn't say recap, this is really the point of this week, or I should say last week when you did chapter 28, and continue that into this week here. But we learned in chapter 28 that when you hook them in series, you add the resistances together. And so a little warning here is the formula for capacitors, we added them together when they were in parallel. So it's easy to get capacitors and resistors backwards. Luckily, on the first test, you didn't have that issue, although some of you were in circuits and had already been introduced to that. And so some of you got it backwards. And I don't know if you were also in circuits, but I suspected that was the case. So my little warning for you is we learned that capacitors in parallel you add to get their equivalents. Resistors in series you add to get them. And so that's what this problem is. This problem is saying figure out what the equivalence is and measure it. Okay? So I'm going to make 3 columns here and say, all right, the first thing to do is called a calculation. Let me not actually do the calculation. I will leave that for you to do. But I will say that I'm about to hook up these 3 resistors that we just used in step 2. I'm going to hook them in series. And so go ahead and take the 3 values and add them up. Of course, that kind of leaves us with a dilemma. Do we use the one from the professional or our homemade one? Why don't we do the professional one, thinking that that's more accurate? Okay. Although we are going to compare it to the professional and the homemade one, so we could kind of do this either way. But just as long as they're close, we begin to see what happens. And so I'm going to encourage you to say, okay, at this point, add these 3 together, and whatever that number comes out, put it right here. And then measure it with our homemade one. So let's measure it with our lab equipment. And then let's measure it with our professional equipment. And of course, all of these would be in units of ohms. And giving myself just a little more room, I'd hate to this part here, but maybe I will, and just put unknown here. But of course, to do our, we need to actually measure L4 and calculate L3. All right, so let me not fill anything in, but have you make this table and fill in this calculated one, okay? Why don't I go ahead and hook up the professional one first, right here, and see what the professional one measures. You okay?
I'm not hearing anything.
Oh, no sound?
No, I do. My ears is plugged up.
Okay. All right, you hear me now?
Yeah, okay.
Okay.
That's my ear.
All right, good, good, good. All right. All right, so guys, let's hook up these 3 and go to the professional one here. All right, so bring the camera over here and say, all right, let me disconnect from my homemade ohm meter, and let me connect these in series. And so here's where I'll need a couple of wires. And of course, series means that they go from one into the other. So if I start here and call this, well, maybe I better start with what I called A, and then go to B, and then go to C. So if I start here and it goes through A, after it goes through A, I'll just make the current go back to the start of B. It goes through B, and once it gets to B, it goes into C, and then comes out here. So from here to here would be a series circuit. It would go from here to there to here. So there's my series. And to use the professional meter, remember, I'll just say it again, an ohm meter, okay? So maybe I'll turn it off first. If I pick this up for the first time, this DMM, this digital multimeter, I would say, okay, what 2 wires do I have? So there it is for the ohm meter. And I would go to the ohm setting. And then I'd have to ask myself, now is an ohm meter hooked in series or in parallel? And of course, it's parallel. And would it be hooked with power on or disconnected from the circuit? Or connected to the circuit or disconnected? And so disconnected. So here I have it disconnected from the circuits. And so I can put my first wire here at the beginning of resistor 2A, and I can put it at the end of resistor 2C, and I get 130.3. And so I'm going to write down 130.3 ohms. So it went down to a 1 ohms is what you got. And roughly, if I calculate these, That's what, 90, 120, 129, 130.1. Whoa, is it really exactly that? Nice. Okay, so that is what they mean by verify. That I have just confirmed by measurement that the resistance of 3 of them hooked up in series is the same as I would get if I just calculated that. And so that's really what they're after. Now, also, let's measure this resistance using our homemade one. So let me take the professional one and disconnect it. All right, so disconnect the professional one. And let me come over here to my homemade ohm meter. And now remember, we would go from the 2 ends of the series. That would be all 3 of them in series. So now my homemade one is designed or connected right now to get all 3 of them. So I need to find out what is the L4. Did I put that in the same order? Good. And so let me tap it down and turn it on, and it goes way positive. Tap it down. Oh, and kind of jumpy here. But it looks like right there is a 0. And so that is a 74.2. So 4.2. I'll let you guys go ahead and calculate L3, and from that, using our working formula, gets what my homemade one does. And I'm not even going to mess with it. I'm going to trust that that's right on, and I hope I am, or at least something close. And so you'll see that they do match. And again, this is the confirmation that they're asking for, that your resistors in series, when you calculate them, it does match reality. And you've measured them in reality. You've measured them not only with your homemade one, but with the professional one. So let's also do the same thinking in parallel. Okay. Now, going back to chapter 28, so last week, we learned that the equivalent resistance when they're hooked in parallel is the reciprocal sum. And so we would have to add the reciprocals all together, then take the reciprocal of that in order to get the equivalence. So I will leave that to you to calculate it. And so what you want to do is fill in this part of the chart right here and say, okay, what does it calculate out to be? And again, you can use these 3. And so use these 3 resistors, put them in here, do your calculation, and come up with, okay, what is it equivalent to? By the way, if you remember from the video lectures, I pointed out that when you do reciprocal sums, the result is always smaller than the smallest. Just like when you do a summation, the result is always bigger than the biggest. So up here, I would expect to get something bigger than 58. And then down here, I would expect to get something smaller than 30. But I'll let you do the calculations. And as tempting as, and as interested as I am in doing it, I'm gonna pass on that. Because once you do the calculation, like we did before, here's the idea, is to measure it, to see if what we measure actually matches what we are asked to calculate in class. Does the real world match our textbook world? And so let me start off by doing the professional one. So let me come back over here to my 3 resistors. Let me, first of all, just disconnect my homemade ohm meter and then hook these 3 in parallel. And I think I'm going to need a couple of more wires to do that. And so if I take these 3 and maybe I do something like this, I would say I have now connected the beginning of the 3 of them all together. And that's what we mean by parallel, that the current can come in here and then it can split off and go to any of these 3. And once it goes through either one of the three, and so when we have billions and billions of charges flowing, some will go through number 1, or A, and some will go through B, and some will go through C. All right, so some go through here, here, and here. But then they'll all regroup and come out here. So my resistance I want to measure is from here, the beginning, to here, the end. So I will put those 3 up here and reach over for my professional ohm meter. I'll say it again. An ohm meter needs to be hooked up in parallel with what you're trying to measure, as well as without connected to power, and that's what I have. And so I can plug it in here, and plug it in here, and say, okay, what is my professional meter telling me? And my professional one is giving me 13.8. So I'm going to write down here 13.8 ohms. And of course now the last part of this one is, what does my homemade ohm meter, my Wheatstone Bridge in this case, give me? All right, so let me disconnect my professional one and just kind of move it off to the side. Let me take this homemade one and put it in this spot, which we keep calling R2. And so, you know, everything else stays the same. So I'll connect it here and connect it here. And let me just do a tap switch. Whoa, very negative. Very negative. And so it looks like it's going to balance somewhere. Somewhere. Still positive. Connect. Come on. Connect. Yeah, still negative. Okay, now it goes positive. And I'm going to say right about there. Okay, so that looks like 24.8. All right, so 24.8 is this F4. And since that one was kind of jumpy here, let me real quickly take the 24.8, divide it by the L3, multiply that by the 45. Okay, and I get a reasonable number. Okay, so kind of happy with that. And I'll let you do the calculation here. All right, so there's step 3. Let's continue on here. Step 4. Step 4 is kind of like we've been doing. It says in step 4, determine the resistance of the coils that are provided. And they're talking about this equipment. This equipment has 5 coils. There is coil 1, coil 2, well, they label them A, B, C, D, and E. Okay, and they're just some wires wrapped around. They're really long. It's hard to tell how long they are, but fortunately, it is written on the back that coil A is 10 meters, coil B is also 10 meters, coil C is 20 meters, coil D is also 20 meters, and the last one, coil E, is back down to 10 meters. So we have 10, 10, 20, 20, and 10 meters for the length of each of these. 10, 10, 20, 20, and 10. Okay, so that's the length of them. They are made out of, and the A through D is made out of copper, and E is a copper-silver mixture. No, I'm sorry. It's a nickel-silver mixture, not a copper. Yeah, it's a nickel and silver mixture. Okay, but what it says is essentially do the same thing that you've been doing back in step 2 and find these resistors. All right, so grabbing my marker here and maybe continuing to leave this on the board. Although, will I have enough room? I'll just leave the equation here. Let me grab my eraser and let's work on number 4 together. And number 4 will fit right here. And so number 4. And like I did over there, let's call this resistor 2A. Or will that be confusing? Maybe I'll just put over here, these are coils. Okay, so this will be A. Because they are labeled on here as A, so let's call that coil A. Coil B. Coil C. Whoops. Coil D. That's what I meant earlier by R2, D2, 2, because we would have had one there and this would have been the second one, so it would have been an R2, D2, 2. Anyways, but R2E. Okay, so these are our 5 coils. And like we did over there, let's measure them with our homemade one. And to do that, we need to get L4 and L3, which we will do centimeters for their lengths. And we will then end up calculating the resistance in ohms. There is one thing different here in step 4 that is different than step 2, and that is they don't say to measure it with the professional one. The professional one is not accurate for values down around 2 ohms or less. And so that's part of the manual description. And so because of that, if we tried to use the professional one, they probably wouldn't match. And you probably would think your homemade one is wrong, but it really is the professional one here. So this is really a good way to measure really low resistance, because most of the professional ohm meters, it's really difficult to do that. And so we as a scientist, we have these really low ohm resistors and parameters. This is how we do it. Seldom in engineering do you come to resistance that low. So again, the meter is probably more useful than for the... I mean, when you're that low for the resistance, usually in a circuit, for example, you just say, oh, just don't even count it as any resistance. It's like taking this wire. We usually just take this wire and say, there's no resistance in here. Oh, that's what we did here. We said, it's so fat that the resistance is so small we can ignore it. And that's not quite true. But that aside, let's go ahead then and actually try this. Now, if you remember earlier in the lab, I said that our measurements work a little bit better when the one we're trying to measure, the unknown, is somewhat close to the known. Because when you do that, your lengths are about the same. If these are significantly different, then these are significantly different. And if these are different by, say, 100 to 1, that means I would be measuring something like 99 centimeters on here and 1 centimeter on there. Well, it's kind of difficult to measure something as accurate as a millimeter on here. So if this was supposed to be off by 1 centimeter and I make a mistake by 1 millimeter, that's a 10% error. If I'm off by 2 millimeters, which I could easily be off by 2 meters, I get a 20% error. And so this is why I was saying this homemade ohm meter is got a lot of problems if I am trying to measure a resistance that is significantly different than my known one. And so I've been measuring things that are near 45. You can see back here, I measured things that were in the 30s and in the 40s and in the 50s. But now you're asking me to measure a wire. And the wire is going to have a resistance of around 1. Some of these are under 1, some of these are more than 1. Which is why I am now going to take my standard one and switch it to 1 ohm. And so know this, as we start to do our calculation, I need to use 1 ohm for the known ones in this calculation, not the 45. Okay. And of course, over here, where I use my homemade ohm meter, let me disconnect my last connection. Oh. Oh. Oh, I see what I did. Let me get this over here. But these were supposed to be together. Okay, so let me disconnect those in parallel. And so this is the connection of we want to find the unknown. So let's start here with the unknown of coil A. And remember I said this is a copper wire that is 10 meters long. Now I haven't told you how thick it is yet, but I will soon. Okay? Because B is also 10 meters long, but it's got a different thickness. So that's going to be the difference between A and B. Okay? So there it is. I think I have my homemade ohm meter set up. And so now it goes positive, goes negative. And if I carefully adjust it until I get a null reading, okay, come on, be nice. It's a little sketchy here, but we are measuring some pretty low resistance, and I think that's why. But it looks like I got a 33, I'll call it 0.7. So 33.7, and like I said, go ahead and from that get L3, and then go ahead and get the resistance by using this calculation, but remembering for part 4 here that you need to put 1 ohm in there. And you can kind of see roughly by the numbers, you're looking at 1/2. And that's what I remember. So I think I did that one to what we normally get, and that is the resistance of this first coil is about 1/2 ohm. And so with our professional one, I'm not even, like I said, I'm not even going to try our professional one. It won't compare. All right, so let me go to coil B and do the same thing. So coil B, as I said earlier, was also the 10 meters, but and I will show you in a little bit, B is a lot thinner than A. So I expect to get some higher resistance here, and sure enough, whoa, goes really positive. Still quite a bit positive. And so somewhere in this category, so it's negative, 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 right there. Oh, too far, positive right there. So that looks like 67.7. So 67.7. And so again, go ahead and put in the L3, and then from that get the resistance of number 2. And again, you can see by the numbers, that's going to be about 2 ohms. And so we've got a thinner wire, same length, the 10 meters, but a thinner wire. Now, let's go to coil C. Coil C, as we said earlier, is twice as long as A. I believe Isn't that what I said? Coil C, yes, 20 meters. But it is also the same thickness. We'll talk about the thickness of it. So I kind of suspect that coil C, being twice as long as A, should give me about twice the resistance. So remember last time we got a half. So I bet this is going to come out to be somewhere around 1 ohm. And of course 1 ohm would be somewhere around these two lengths being equal. So I probably am going to balance somewhere around the 50 mark. And so sure enough, right there, looks like the balance. And I am at 50.4. And so 50.4, and of course that would make very close to 1 ohm. And likewise, coil number or letter D is like B. It's twice as long as B. It's the 20 meters. Let me just double check. D is 20 meters, yeah. But it has the same thickness. Now, if you remember on B, what I said, we got about 2 ohms here. And so this is probably somewhere around 4 ohms. So let's see. Wait, am I going the right way? Ooh. Okay, I'm thinking coil D is not working right. Let me just try a conduction meter here. Oh yeah, my coil D not working right. Let me grab another one. Oh, I can get it, Ron. Thanks. It's close by. I have another one sitting over here. Let me grab this coil D hand so I don't get tricked. This one beeped at me. That's the multimeter as a conduction meter. And if it makes a connection, it beeps. So I put it in a conduction mode. All right, so let's try this again. And let me put it maybe somewhere about here. Oh yeah. Oh, right there. And so that looks like an 81.5. I like that because if that was an 80, that would be a 20, that would be a ratio of 4, and so coil D has about 4. It looks like it's going to be a little less than that. No, a little more than that. So it's probably double of what that one is. Now, coil E is something totally different than any of these because it's not copper. It still is 10 meters, I believe. Let me go back to the one just so I'm consistent over here. But this is mostly a nickel, but it's got a little bit of silver in there to help for a lot of reasons. One is the oxidization and the other one is the conductivity of it. So it actually conducts a little bit better than nickel by itself because silver's a really good conductor, and so you kind of mix it, you kind of get a blend between it. But it's only a small percentage of nickel, and I don't know how much. So we're not really sure what its conductivity should be, but I do know that coil E is 10 meters long and has a thickness of A. So coil E is about what A was. Now remember, A probably is somewhere around 1/2. I haven't done the math here. But this right here then is probably something greater than 1/2 because it's mostly nickel, and nickel doesn't have the same conductivity of copper. So maybe it's 1. I really don't know. And so I shouldn't even guess. I should just get out my meter and give it a try. So I'll hook up my homemade ohm meter here and maybe put it, well, I'll put it at the 50, that would be 1 ohm. Whoa. And so it's a lot higher than I was giving it credit for. We're looking at about a 9-to-1 ratio, so about 9 ohms. And so this is 89.5. So 89.5. So it's about, like I said, 9 to 10 ratio. That's 9. 9 times 1 is about 9. So this is going to be somewhere around 9. And I guess that makes sense. This is then 18. Let's see, this was a half, right? So 9. So roughly, if I remember these off the top of my head, I shouldn't even talk. I'll let you guys calculate them. But that is going to really show how nickel is a much poorer conductor than the copper. Looks like about a factor of 18. Of course, it's not pure nickel either. So that's why when we get to step 5, you'll see what I'll do here in our last step. So here's our last step. Our last step in number 5, it says use the information on the back. Okay, so right here on the back for the coils that are made out of copper. Okay, so that's A through D, so we won't worry about E here. Well, no. They asked to do it, we just can't really compare it. Here's what I mean by that. I should just keep talking, but look this information up. And so number 5, and our last step and your last calculation here for this homemade ohm meter is to say that the resistance is equal to the resistivity times its length divided by its cross-sectional area. What that means then, if you take the resistance, you multiply it by the area, you divide it by its length, you're going to get the resistivity. And so step 5 is saying find the resistivity of each of these 5 coils where we got its resistance. So taking the resistance in number 4 here, okay, you can put that into here. The things you're going to need to know, though, is what is the length and what is the area. Now, maybe I'll take one more step. The area is pi r squared. Actually, maybe I'll even go one more step, because the radius is the diameter over 2 squared. So if I take this radius and I square it, the diameter over 2, I get diameter squared over 4. Okay, so here's what you are going to do with your calculator. You are going to take the resistance you got for each of the 5 coils. I'm about to show you the back of this, where it gives you the length and the diameter. This will also introduce you to what we call the American wire gauge, the AWG. So we'll get a chance to see some engineering numbers here. And we're going to find the resistivity. So your job is to find the resistivity of A, the resistivity of B, the resistivity of C, the resistivity of D, and the resistivity of E. Now, by the way, let me just repeat that A through D are all copper. Okay? Your author even reminds you that not only should these be the same, but he writes down that the resistivity of copper listed in your textbook is 1.72 times 10 to the minus 8. So let's see how close we get to 1.72 times 10 to the minus 8. Now, for this last one, we can't really know what we're supposed to get. We can look up nickel, but it's not pure nickel. So I guess we could look up nickel and see that we are better than, or by resistivity I mean smaller than pure nickel. Huh? Oh, yeah, and I guess I should be careful with the units. This should be an ohm times a meter, I believe. Let's see. Ohm and then meter squared. Yeah, ohm times a meter. And so that'll be your units. Especially if the fact that we got to do this in meters. So I will let you calculate them, but let me give you the lengths. And let me give you the diameter. So I believe I said 10 meters, 10 meters, 20 meters, 20 meters, and 10 meters. And I'll just double check that. 10, 10, 20, 20, 10. Okay. The diameter, though, is kind of a fun discussion to wrap this up, because they say that it has a diameter of, and it says number 22 gauge. It's called the American wire gauge system. This has number 28 gauge. This has number 22 gauge. Let me pause right there, because I said earlier that coil A and coil C are essentially the same diameter. There they are, they're both a 22 gauge, but that the length of C is twice the length of A. That's why over here I was kind of expecting that if this A came out to be nearly a half, this would come out to be a 1. Now as I continue on, this says number 28 gauge. Again, that's why I was saying that B and D are really the same diameter, but D is twice the length of A, and so hopefully the resistance I get in D was about twice that I got in B. And I think I got roughly a 2 for B and then roughly a 4 for D. And then the last one, the oddball one, the nickel-silver mixture, has a gauge of 22. So we just have some wires, 22 and 28 gauge. They're kind of our most common ones here. But with that in mind, then, did I bump this or anything? Okay. Let me go ahead and turn towards the end of this lab. It's on page 26. It's a photocopy out of one of the zillions of engineering handbooks. And so you can look up, and it says here the AWG, what is called the American Wire Gauge System. And sadly, the different manufacturers are a little bit different, but we buy our wires from Brown and Sharp, or at least they're standard. I don't think they're in business anymore, but they kind of standardized this way back in 1857. Okay, and they came up with this numbering system, which also represented the diameter. Let me not try to explain the numbering system. It has to do with the way you manufacture it, okay? But know this, that the higher the gauge number, the smaller the wire. So there's an inverse relationship to it, okay? It has to do with the weight, and so you might say it's something like, how many feet do you need to make 1 pound? So if it's a thin wire, you need a lot more feet to make 1 pound. Okay, it's not quite that definition, but it's close to that. So, over to here, what we need to know then is gauge number 22. So if I scan down here, it says here the diameter is 0.644 millimeters. So 0.644 millimeters. 0.644 millimeters. Now remember, the bigger the gauge, the smaller the wire. Again, because you need more feet of it to make 1 pound of wire. Again, don't take that definition too literally. But as I scan down, the 28 is 0.321 millimeters. By the way, it's very similar to the same manufacturing gauge that you would do for nails, if you've ever worked with nails or any type of wiring. Maybe if you buy an extension cord, you go down to Home Depot and you want to get a 100-foot extension cord, and then they have this real cheap one, a 16 gauge, and a little more pricey at 14 gauge, and then getting quite expensive at a 12 gauge, and really expensive at a 10 gauge. Now, of course, the 10 gauge is a smaller number, so it's a thicker wire and it's a lot more copper. And you go to pick up a 10 gauge 100-foot extension cord, and if you're not careful, you're going to throw your back out. It's heavy, and it's a lot of copper, and costs a lot, and is necessary if you're trying to get a lot of current run through there. Because remember, this thicker wire, so the smaller the gauge, you would have lower resistance. That's why some of these are amazing. I mean, look at this. I mean, they counted down until they got to 0, and then they have a 0, a double 0, a triple 0, and a quadruple 0. So the quadruple 0 wire is huge. Look at that. It's 11 millimeters. It's over a centimeter in diameter. It's a thick wire. But I digress a little bit. So I've been talking a lot. I hope that this made sense. Let me just go quickly to the questions, because what I want you to turn in then through Canvas is kind of the answers to all of this. And so, fill in the calculations for Table 2, for Table 3, for Table 4, and then eventually all these resistivities for Table 5. And like I said, if you're doing coils A through D correctly, you should get that number for copper, and probably a number like 18 times higher than that for the nickel, the nickel-silver mix, somewhere in that ballpark here. But let's take a look quickly at the questions. I think you can answer the first one. It says, what is a null detector and how was it used in this experiment? Remember, a null detector is when you make your measurements when you're drawing no currents, okay? And so there's a null reading. That doesn't mean you don't learn anything, but in this case, our circuitry, our galvanometer has 0 current when we make a reading, and we made a distance reading. What condition must be satisfied for resistors to obey Ohm's law? Maybe I should say that one again. This is probably really a more appropriate question for 2 weeks ago. But if the resistance stays constant, even as the temperature warms up, we say it technically obeys Ohm's law. But we have the lighter form of Ohm's law that we just say, oh, it's just the resistance has just changed. So not a very good question there, but it's the same question that was asked 2 weeks ago. 3 says, compare the calculation of the 3 resistors connected in series to the value measured with your Wheatstone bridge, and what's your percent difference. So in series, so they're going back to step 3 there, and I think you can do that. 4, show your calculations for the resistivity of copper. You might have already done it by this time, using the data taken from the, now this says from the commercial Wheatstone bridge, calculate the percent difference. Let me change that a little bit. We used to have a real nice professional one on the side to kind of see how things would work. We don't. So I'm just going to say, change this question to how close did you get to that accepted value that I put out there. So let's take that as our accepted value. Now it says in 5, if the temperature of the coils to increase during this experiment, what do you think would happen to that resistance? And so in case you didn't pick it up way back in chapter 27, for metals, we expect the resistance to increase. Right? If you go back to chapter 27, you'll see that temperature coefficient is a positive number. I should point out, and I know I did it in the video lecture, that some have a negative. In fact, all the semiconductors have a negative. And I explained in the video lecture, so let me not do it now, but why the resistivity actually decreases with temperature for these semiconductors. And that's good and bad, and I'll leave it alone of what's neat about that engineering. But thermal runaway can really be a problem with our semiconductors, because if something goes wrong with, say, your computer, your electronics in there, and it gets too warm, too much current, gets too warm, that's going to warm it up, and actually the resistance goes down. And so because it goes down, the problem gets amplified. That is, you had too much current, now you have even more current. And that makes it even hotter. And as it gets hotter, that makes less resistance and even more current. And it's what we call thermal runaway. Once something goes bad, it goes really bad. It just gets worse and worse and worse and worse. So our modern day electronics has a serious flaw in the sense that it's not self-correcting. When something goes bad, it just continues to go on the bad side. It would be like an unstable equilibrium. It would be like putting a ball on the top of a hill. If you get it right on the top of the hill, it stays there. Everything's perfect. But boy, you get it off just a little bit, it just keeps getting worse and worse and worse. It rolls down the rest of the hill. It's not a stable equilibrium where if you're in the bottom of a gully and you move off a little bit, gravity pulls it back. And then if it goes too far, gravity pulls it back. And so it's self-correcting when it's in a stable equilibrium, and it's seriously problematic when it's in an unstable equilibrium. And our electronics is that way. We're in an unstable equilibrium when it comes to our temperature. So when things go wrong, it just goes, oh, well, I guess that's done. And it's so much cheaper to actually buy new than to fix with today's throwaway electronics. So we just recycle it and move on to the next one. All right, well, turn those in and we will see you again in the next lecture or in the next lab. Take care.